That is much better. We can see your screen and hear you.
I had to hit one more button, sorry. Okay,
No,
so what I'm going to talk about, and before I get going here, I'll just say that I have too many slides here with too many equations. And the good news is that this is all published. And so I'm just going to point everybody to a publication to answer essentially questions and to go over some of the derivations that I did up to a decade ago. So the publication will do a much better job of telling you what we did than I could right now anyways. And so this is work that we've been doing over the last 20 years at the US Geological Survey, and mostly using Nortek instruments, but we've also used, and these are horizontal profilers, which we call acoustic Doppler profilers for short, ADPs. We've also used instruments from OTT and Sontec as well. So we have a pretty good experience with a number of different manufacturers on this. The photograph here just starting to shows a deployment with two Nortek instruments. One is actually an EZQ, a 2 megahertz EZQ, and the other is a 1 megahertz Aquadot. And this is on the Green River in Colorado. Let's see, how do I advance? I guess I click it. Okay, sorry about that. I'm not very good at Zoom meetings. So why would you want to do this? So first of all, when you're working in rivers, in most rivers, there's not a unique relation between the discharge of water and sediment concentration. So if you're interested in knowing the sediment loads for silt and clay or for sand, historically people have used to use continuous or daily measurements to get this in the US Geological Survey at a number of sites around the country. And because of the expense of that over time, people started using rating curves, but you really can't do that because there is not a unique relation between discharge and sediment concentration in most systems. This is an example from the Sacramento River in California, showing basically during the rising limit floods, you both have higher concentrations of silt and clay and sand than you do on the recession. And the reason for that is during flood events on this river, you're basically running out of sediment. And that's exhibited by the fact that you have coarser sand sizes as you're depleting the sediment supply during the flood on the recession you do on the rising limb, which is giving rise to this loop of concentration. In other settings like the Mississippi River, you have a similar process, but it can be driven by a completely different process in the river per se, in the sense that you still get hysteresis and sand concentration and silt and clay concentration during floods. This is actually driven for silt and clay by running out of silt and clay during the flood. But for the sand, it's a completely different process. You're not running out of sand, but what you do have is you have effectively larger bed forms, larger dunes on the bed of the river on the recession, relatively speaking, than you do on the rising limb. And because of that, you have more drag on the recession than the rising limb, and you actually get hysteresis and sand concentration, even though there's plenty of sand available in the river. And that's exhibited by another kind of grain size associated hysteresis, where you're running out of sand during the flood, but the sand on the recession is actually finer because of the greater drag suspending less of the coarser material into the flow. So in other words, you basically need to measure sediment transport continuously in rivers if you really want to have accurate loads. And for that, at least over the last 20 years, we've been turning to multi-frequency acoustics for the most part. We also have used a lot of optical techniques. I'll just say this right now, is one of the reasons why we've turned more to acoustics is that there's far less maintenance associated with using acoustical approaches than optical approaches, mostly from fouling. Fouling of acoustical instruments in rivers is not nearly as big a problem as for optical instruments, and not nearly as bad as the marine and estuarine settings we've been seeing examples of. In any case, these are the places we work around the United States, mostly in the Western United States, but also in Wisconsin. The blue dots show deployments where we have two arrays of 2 frequency ADPs. The red dots show where we only have a single 2 megahertz frequency instrument. And this green dot is where we have actually 3 frequencies. We have 2 megahertz, 1 megahertz, and 600 kilohertz. For the most part, we tend to prefer using paired 1 megahertz and 2 megahertz instruments. And all the data we collected, and these are all 15-minute data, are available at this website right here. Just to show you what this looks like, I'll show you some examples from some data that we've collected at this station in Grand Canyon. This is the Colorado River in Grand Canyon. This yellow dot shows the location of the station where we have a 1 megahertz and a 2 megahertz ADP. They're both aquadopts now. They started out being EZQs. Just as a side note, in terms of longevity, at a station located right here, we actually had an EZQ deployed for 10 continuous years underwater. It never came out of the water. And we did collect data every 15 minutes for that 10-year period. That's probably our champion. Usually we have something like a lightning strike or something else that happens that takes out a power supply or something else happens. But we've had quite good luck especially with Nortek instruments. And so we do have this one example that that Malcolm was always very excited to hear about because it never came back to him for repairs and it was there for 10 years continuously. So at our website, you can see data look like this, and this is just an example. I'll just show this is discharge of water over time. This is in cubic feet per second. I'll be flip-flopping between English units and SI units. That's the way we roll here in the United States. Anyway, so this is going up and down every day, not because of a tide. Well, it is a tide, but it's a tide caused by an upstream dam. And so we're seeing daily fluctuations in discharge that are driven by dam operations. This is silt and clay concentration that's measured using the acoustical instruments, compared with actual real samples of the velocity weighted silt and clay concentration that we've actually collected using real samplers using our traditional techniques in the USGS, and also pump samplers in blue, where we've calibrated those as well to these traditional measurements in orange. So you can see there's a big pulse in silt and clay here. This is actually caused by an upstream tributary flood. Here's sand concentration over the same period, with green showing the acoustical 2-frequency instruments compared with the sample data. And you can basically see this basically going up and down every day with discharge of water, but there is some variability driven by changes in particle size, which is shown here. So this is the median grain size of the sand, green being the acoustical measurements with the samples. So you can see basically we had a decrease in particle size here associated with an upstream addition of new sand, and then it coarsens over time. And then right when this tributary flood caused this big spike in silt and clay here, it also caused the sand grain size to fine because we're adding new sand to this river upstream. So the sand grain size goes down and then basically slowly coarsens. And you can also kind of see the daily cycles here associated with sand concentration going up and down in this grain size plot. So that's what our data look like when it's processed. Everything I'm going to cover here, or try to cover in the next 20 some odd minutes, is in this publication. It's 108 pages long. I recommend anybody interested in this should just go to this, where we have all the theory that's underpinning this stuff, as well as all the analyses that I'll try to gloss over here in this next period of time. This is just an example out of the river of our 3-frequency array as it existed some number of years ago with EZQs, and this was an aquadopt. Here now we have actually 3 aquadopts at this site. 10 years seems to be the limit on instruments, so we've been doing this longer than that now. So a brief summary of the method is this. We use acoustic attenuation to estimate the suspended silt and clay concentration in the river cross-section. The grain size distribution of silt and clay is estimated on the basis of agreement between the measured and theoretical attenuation concentration and backscatter concentration relations at all frequencies at a site. At each frequency, backscatter then corrected for the backscatter from silt and clay, which we actually have B prime, which we call excess backscatter, because all sizes of sediment contribute to backscatter, not just sand, as some people assume, is used to estimate the suspended sand concentration at assumed reference D50 of the suspended sand characteristic for that site. And then using theoretically predicted relations between sand D50 and the target strength, suspended sand concentration at D50 are solved for such that the B prime excess backscatter corrected backscatter, so that's the backscatter from silt and clay, is removed. And then we use each frequency in our array to basically solve for one sand concentration and median grain size iteratively. And now I'll just talk about where the error comes from. So in terms of the error in the acoustical measurements, the largest source of error isn't actually in the acoustical measurements per se, but is the fact that we're actually subsampling the river cross section. So this is a river cross section. This is just a cartoon of a acoustic Doppler profiler with a sonified region out here. So here's where the beams are. This is a picture of a cross section where we have these things. And so the cross section here is 94 meters wide. This is my team out there collecting the actual samples across the cross section used to calibrate and verify these instruments. So we have a 1 megahertz instrument, which basically insonifies out 28 meters, and a 2 megahertz instrument, which insonifies out 11 meters. And so you're really subsampling. And so most of the error in our measured suspended sand concentrations, suspended silt clay concentrations, is from the subsampling effect, because you're basically assuming that this insonified region is representative across a pretty wide range of flow and sediment conditions for what's going on in the cross section. And that error may not be random. And so really, depending on the quality of your site, how well mixed the cross section is, things like that, you can get substantial error, but it's not necessarily from the acoustical measurements themselves, it's from extrapolating to this whole cross section. So we've already heard all about this, so I'm just going to gloss over this, but basically the target strength is what we're going to focus on. Also to some degree this, because this is the term in the sonar equation we use to calculate the silt and clay concentration. This is really what we use to calculate the sand concentration and grain size corrected for silt and clay concentration. This is what the actual instrument measures in terms of what you're, when you download the instrument, look at, this is what you're getting. And I just want to basically say in this publication I talked about, we go through this in detail. I'm not going to even try to say much more about this besides the fact that there's a pressure version of this that people are familiar with, I'm sure, to some degree. This is the active sonar equation, and you can go back and forth between the two, and we do in this paper. Basically, what I've done here is essentially color code the terms to show where they go. So the source level shows up here in yellow. The reverberation level shows up in a few places. The two-way transmission losses show up here in blue, and the rest of this really is the target strength. Now, the target strength has two pieces to it, essentially. One is related to the sediment, and one is related to the reverberating volume. And so for the sediment, basically, it varies as a function of the concentration, the grain size distribution, and the density. So we use attenuation to estimate the silt and clay concentration. Basically, we have alpha sub S and concentration. Alpha unit is basically what we call the combined ensemble average viscosity and scattering loss attenuation coefficient. And this is really derived in the same way that Stephanie Moore did in this publication. And so at certain frequencies and sediment conditions, basically the silt and clay alpha unit far exceeds that of sand, such that you can basically assume that attenuation is driven mostly by the silt and clay concentration. Now there's some caveats to that. So this is just a plot of the D50 of sand or sediment in suspension rather. This is alpha unit with some goofy units on it. Basically just showing you for different sortings, as you basically go from a very tight distribution to a very poorly sorted distribution, how the peaks in the viscous scattering loss, or the viscous and the scattering loss ranges are change. And so basically what you see is that when you have well-sorted sediment, be it in silt and clay size or sand size, you have these big peaks, which decay as the sediment gets broader. It also depends on the sediment density, which is really largely whether or not you have quartz density, chloride density, or something with a lot of montmorillonite for at least the silt and clay size of things. And it also varies with frequency. And the key thing here is that as you go to lower and lower frequencies, you basically end up doing better in terms of making the assumption that most of your attenuation is actually caused by the silt and clay. And so when you plot this up at different frequencies, this is all at one site in the Colorado River, you basically have silt and clay concentration going from 0 to 35,000 milligrams per liter in each plot. You basically see that you can actually get really tight regressions forced through the origin, and also from theory here basically for this kind of silt and clay grain size distribution and density, which is what the red line is derived based on for all of these. You also can see that at the highest frequency here, what happened there? Okay, at 2 megahertz, you basically get less good results in the sense because for this little cloud down here, you get quite a bit of contribution of attenuation from sand-sized particles. And so that effect goes away as you go to lower frequencies by and large. So as the sorting of suspended sediment decreases, the target strength also for this finer sizes approaches that of sand. Now the unit target strength is basically the range independent target strength. So we've basically gotten rid of the range terms, which if you go through the detailed derivation, there's a range term that's actually in the target strength, which ends up typically being combined with the transmission losses. And you'll see how it's done in that paper. And it's also for a concentration of 1 milligram per liter. The key thing here, though, is the grain size distribution broadens. Basically, you can see that the silt and clay size sediment has just as much backscatter, if you will, as the sand size sediment. And so for the type of sediment that contributes to backscatter, it can be any size, really, depending in terms of how broad the distribution is. And for well-sorted sediments, basically the sand is more important, but in rivers, you typically don't have a situation like that. There tends to be silt and clay and sand together. So what I'm going to basically do here is skip over this as well. Basically just say when you look at this kind of derivation that people are somewhat familiar with probably here, this kind of equation is only appropriate for really tight distributions where you have one grain size of sediment. As soon as you have a grain size distribution, there are many more terms that come in here. And so to basically move forward with our method, we basically derive calibration relations for a constant grain size, so a D50 reference size, and we also exclude the high concentrations of silt and clay. So we basically derive this equation, and all this stuff here is buried in these other terms that you can read about in that report. When you do that, you get relations like this. So this is the log of the sand concentration, and this is the beam average backscatter at these 3 frequencies. These are all for a very tight grain size distribution of sand at 0.125 millimeters for a D50 with very little silt and clay in suspension for these conditions. So when you basically have almost no silt and clay, so less than twice as much silt and clay as sand is what this means right here, you get quite nice relations. These are what we call our base backscatter calibration relations. Now, I just want to basically use this as an example here. It'll vary between frequencies here, but as you basically get coarser and coarser sand, not this size, basically the points would drift off to the right in this space. Finer sand in this size would go to the left. That effect is greater at the 600 kilohertz frequency and lower frequencies than the higher frequency for reasons I'll show in the next plot. Also, the other thing that you'll see is that if you have much more silt and clay in the water, you get points that drift way off to the right. So this is almost no silt and clay in a very tight sand grain size distribution. Silt and clay also contributes to silt and clay, and you can basically use theory to derive something here, and this is our B prime definition. And we can actually have a theoretical plot for different conditions of silt and clay versus sand plotted as a function of the ratio of silt and clay to sand in suspension. This is all in that paper ad nauseum. I'm not going to even attempt to go through it, but I just want to show you right now that this right here is the ratio of silt and clay to sand in suspension going from very small amounts to much more, 1,000 times more silt and clay than sand here. This is our B prime that we defined in that previous slide. This is the theoretical curve. These are the sample data right here, basically showing you that at this point here, you can actually have 30 decibels of backscatter produced by the silt and clay when you have 10,000 times more silt and clay than sand for this condition. This variation here is because the grain size distributions of the sand size sediment and the silt and clay are not constant here. So basically we're assuming constant distributions to derive this red line here. When you look at it, as I showed in these other plots where you have basically log of concentration of sand and this backscatter on the x-axis, for different conditions where you go from 10 times or less silt and clay to sand to over 10,000 to 20,000 times as much silt and clay as sand in suspension, and this is the theoretical lines here. You basically see what I was saying, which is basically the points just drift off to the right of what we call our base backscatter calibration relation, as you have much more silt and clay in the water. And so to continue and to try to wrap this up, basically we account for the silt and clay in suspension using attenuation. So we basically use the attenuation to estimate the silt and clay at the different frequencies. We then use that information to account for the backscatter from the silt and clay, assuming a reference grain size for the sand. Then we move forward with that information to solve the results iteratively among the frequencies with this in mind. So as you go from the 600 kilohertz to 2 megahertz range in frequency, basically what you find is that in the sand size range, there's a huge difference in what we call our relative unit target strength. And so basically the change in the sand median grain size has progressively greater effect on target strength at progressively lower frequencies. And as a result of this, if we use a theoretical form function, the one that we tend to use is that of Thorne and Morrall 2008, we can actually solve for the sand concentration and sand median grain size using these theoretical relations that'll allow us to have a concentration and grain size that satisfy the results that we're getting from our two instruments from the measurements. And in one case, we have 3 frequencies at this one site I was talking about. When you look at the theoretical values using what we call the relative unit target strength, and that's really just relative, meaning we've gotten rid of, it's normalized essentially. So basically this is the relation from theory at a 2 megahertz frequency. And I basically plotted up sample information from the cross section in 3 different concentration ranges, basically only to show there's no real concentration dependence here. So you can basically see that, yes, there's a steeper curve here. As I said, there's more variation as you go to lower frequency. You can predict that from theory. So the relation from theory here compares well against the samples. We use these theoretical relations to then calculate the concentration and median grain size using the 2 frequencies or 3 frequencies. And then when you compare it against the acoustical measurements for silt and clay against the actual real measurements, if you will, from the samples, you get things that look like this, where the error is much greater at lower concentrations, but it collapses at higher concentrations. A similar result for sand. And also it does fairly well for sand grain size too. The one thing just to call your attention to here, there's basically less than 1 order of magnitude of variation here, whereas we have 5 orders of magnitude here. And so this doesn't look quite as good as this, but it's not bad. So this is median grain size acoustical, median grain size from the actual samples, concentration of sand from the acoustical measurements from the real samples there. I think I'll skip over this for now just to wrap it up. But basically what we found is that the 95% confidence interval errors that we derived at some of our networks hold at other sites, so at least our error calculations and the methods seem to be good. The only thing I'll call your attention to here is the black line is the 95% confidence interval in an individual acoustical measurement. So you can see at low concentrations, the errors actually exceed 100%. We get around that problem because we collect 15-minute data so that over many acoustical measurements, the effective error, say over the amount of sand passing a station or silt and clay passing a station over a given day, is reduced because there are 96 measurements in a day. And even though the error in the method is not truly random, it's closer to random than it is not random. And with that, I'll wrap it up. A lot of stuff. All I'll say in my defense is that it's all published. And I'll refer people to that publication for any details. But just to sum up, over the 600 kilohertz to 1 megahertz range that we've made measurements in, attenuation measured at the lowest frequency generally provides the most accurate measurements of suspended silt and clay concentration. When the silt and clay to sand ratio is much larger than 2, the backscatter produced by silt and clay must be accounted for when you're trying to measure suspended sand concentration. Otherwise, you'll get enormous biases in your estimates. When variation in the grain size of sand, D50, exceeds relatively a half phi, 2 frequencies are likely required to make unbiased measurements of suspended sand concentration. You can only get by with using 1 frequency for your acoustical measurements when you have a very, very tight sand grain size distribution. The relative errors in acoustical measurements of suspended silt and clay concentration and suspended sand concentration decrease with increasing concentration. Relative errors in the acoustical suspended sediment measurements we made at other sites behave the same way as we originally found for most of our work, which was done in the Colorado River and the Rio Grande. And the one thing I will say, and again, the source of this error is really the subsampling issue more than it is the acoustical measurements themselves. To the degree the site you're making these measurements has an insonified region, which is more representative of the conditions in the entire cross-section over a wide range of flow and sediment conditions, the less the error, and also the more random the error. So what we have seen is that there is significant positive autocorrelation in errors at some sites. And basically, as I pointed out, it really comes down to your site and how good your cross-section is for being representative of the entire, or how your subsample is representative of the entire cross-section. Sorry about that language problem there. Anyway, that's it. A lot of stuff, but like I said, it's in that paper that I highly recommend. Anybody who's interested in this, get a hold of. You can download it. It's free. And with that, I will end.
Perfect. Write down that link. Okay. There are a few questions. Jeremiah has asked 2, but Jeremiah, just in thinking about time, maybe you can ask them in the breakout room since you'll be in the room with him. So I will ask a different question from someone. When starting at a fresh site, how long does it take to develop a good calibration? How many water samples are needed?
The answer to that question is it depends on how lucky you are with nature giving you a wide range of conditions for flow and sediment. Typically in practicality, we can get working calibrations with a year's worth of data, and typically we'll have, and then we'll revise that over some number of years. Usually after several years, we'll have a solid calibration that doesn't change unless the cross-section itself changes in the river. And we'll typically get anywhere from a dozen, well, half dozen to dozen full cross-section measurements, augmented by probably on the order of 50 or so pump samples that we automatically trigger to get conditions when we can't get out there, because a lot of the rivers we work in have really variable concentrations associated with storms, and they're remote. And so we rely on the pump data to augment those actual full cross-section measurements.
Okay, great. Thank you.